All right, back with part two here, and I've got a proof, and you don't have to write this down. Just absorb some of it, as much of it as you possibly can. Why do I care about proving this if I'm not responsible for it? But again, many of you will be going on to math at school next year, and you're going to be responsible for reading and writing your own proofs. So it's good to get as much exposure to this sort of thing as you can. So if we want to prove that the composition of two odd functions is odd, what are we given with? Well, we're given to start with is that we have two odd functions. And what does it mean for a function to be odd? Well, we've got these properties, right? F at x equals negative f at negative x. And just because I know it's going to suit me in the proof here, f at x equals negative f at negative x. Notice that if I wanted to, I could just multiply both of these sides by -1 and put the negative on the other side. So negative f at x is equal to f at negative x is also the same thing. What am I required to prove? Well, this is how I show a function is odd, right? This idea of if h at x is equal to negative h at negative x, well, the h happens to be a composition, but it's no big whoop. And so I've split this into left side and right side and used the definition of a composition on both sides to get myself started. F at g at x, but g at x is odd, right? So where I saw this thing, g at x, I could put this thing. So that goes in there, negative g at negative x. And when I'm looking at this, I see f at negative something, negative box. F at negative box, well, since f at negative box, since f is odd, f at negative box, there's the box, is equal to negative f at box, then I could write this minus outside because f is odd. This reason right here. And in fact, that's exactly what I have on the right side. Left side equals right side, and a composition of two odd functions is odd, just like we expected. Again, you have to be able to do it this way, and so you can just answer it, but that's the proof, and that's good for getting ready for university. Now, our only example, is this our only example? No, we got a couple of examples. Um, but it's this idea of an application, combining functions, modeling, that's the idea. Solve problems involving the combination of two functions, including problems arising from real-world applications. And we're going to do a couple days of this sort of thing. Forrester Ferd is setting up a moose reservation. He estimates that he can fit that many moose on Q square kilometers of land. He also estimates that the cost of keeping M moose would be that function there, determine and interpret C composed with M at 12. Okay, well, this doesn't sound very hard because this is just a straightforward calculation. This perhaps we'll have to think about. But we just practiced our compositions, so this should be no problem. C composed, why don't I actually do a step here where I have C at M at 12. Now what's M at 12? I'm going to do this in the margin, whereas M is 3 times 12 plus 5, which is 36 plus 5, 41. And then this is 41 I just calculated, so C at 41. I'm going to take out the 41 and put in 41 for M, and then calculate that, bang, 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 on the calculator, 116.4. And what does that mean? That means, well, what was the input? The input was a 12. 12 what? 12 was Q, 12 square kilometers of land. So for 12 square kilometers of land, what's the output? Well, the output, C, is the cost. It will cost $116.4, thousands of dollars. So, comma, 00, thousands of dollars. Hang on. That's not right either, is it? Oh, yeah, that's okay. 3 zeros. 1, 2, 3. It will cost $116,400 to maintain the 14 square kilometers of land. That's the interpretation. Notice that in that calculation, we didn't really talk about the moose, did we? Right? 12 kilometers of land cost this much. The skip function, the part that we skipped was the moose, that there was actually 41 moose on that land. And in that skip function, we kind of missed that moose thing. And that was the idea, one of the ideas behind the composition. All right. So next thing is just to calculate the skip function in general, right? So I've got C at M at Q, and M at Q is 3Q plus 5. And in the cost function, where I had 2.5 M plus 18, instead I have this thing. And then now I'm going to distribute the 2.4 through there, and I get 7.2 Q plus 12 plus 18 equals 7.2 Q plus 30, and that's the skip function. So what does that mean? Well, what that says is for keeping Q square kilometers of land, it will cost $7.2Q plus $30,000. And the whole moose thing is skipped. I've got a function for cost that's directly in terms of the square kilometers. What's next? Last? What's last? Currently, Lemontown Car Sales sells an average of 40 cars per week at an average of $70,000 per car. The marketing department estimates that if the company raises their average price by $500, they will sell one of these. Okay, this is one of these ones where we've got, you know, you raise the price, you'll make more money, but you get fewer customers. And we've seen these a few times over the years. Typical modeling question. This one was a little bit different because we were given the models, right? This one here, we have to come up with it. Almost like the sandbox example from earlier in the chapter, right, where we had to model the cost of the sandbox. We have to model the revenue. We want to end up modeling the revenue. Write a function nx to represent the number of cars sold after x price hikes. So if we raise the price once, we're going to sell 5 fewer cars. Well, right now we're selling 40 cars. 40 cars a week, but we're going to lose 5 for every price hike. Does that make sense? We price hike once, lose 5 cars. Price hike twice, lose 10 cars, and so on. But to make up for that, the SP is the sale price. We're going to be able to make more money on each car, right? So $7,000, but we're going to raise the price $500 per price hike. Leave it alone, we get 0 price hikes, and that's 7,000. One price hike is 7,500, and so on. Okay, dandy. Check. C. Write a function to represent the revenue. Well, remember, revenue, they're business folks, revenue is just a number times the sale price. Is this the composition? No, this is a simple product, right? So if I say R at X is just the product of these two functions, right? The product function, not the composition function, the product function. So I would just take these two individual functions and multiply them. And actually, you saw this example way back in grade 10 because this ends up being a quadratic function. And that's our new revenue function. Great. And then it asks us to use technology to find the maximum revenue. And I suppose we can do that. There's a way actually very quickly, because when the revenue is zero, I can find the x-intercepts, and I could find the vertex pretty easily using grade 10 techniques, but it asks us to use technology. So let's pull out the graphing calculator, pull out Desmos. Which shall we use? I got the graphing calculator here. You could use Desmos though, right? Y equals, clear that off there. What's the hardest perhaps about this thing is figuring out a scale where this is going to fit. 5x. What kind of shape is it going to be? This is going to be a parabola, right? It's going to open 7,000. Did you notice that error? Hopefully you noticed that. 7,000 plus 500x. It's going to be a parabola that opens down. The leading coefficient is negative, right? Starts low, ends low, all that business. If I were to just press window or press zoom something, it's not going to fit on, because these are huge numbers, and I want to figure out the maximum revenue, where it looks like they're making already $280,000 a week. Is it weekly sales? Yeah. So I don't know about price hikes, so I don't know whether it's going to be 10 price hikes. Could I have a negative price hike? A negative price hike would be lowering the price, and if that meant more customers, that might mean more revenue. So yeah, let's include some negatives, and then I'm going to look for the revenue, and I don't think the revenue will be negative, but let's get some numbers in here. And this is going to go all the way up to, might go all the way up to $300,000, right? So I just want a little bit of negative so I can see the axis, okay, and then I'm going to put in $300,000. And I'm going to have the scale as $50,000. This is the hardest part, I think, is just to getting your graph to fit on the technology. Oh, look, it got cut off. There's the maximum. In fact, what's nice here, on Desmos, you just click on that and it would be perfect. I don't think it would make that sound. But for the graphing calculator, I go calc, and then I want to find the maximum. Go to the left of the maximum, way over here. Oops. Oh, cancel. Go to the left. Left. Am I to the left? There's the spider. Yeah, I see the spider. Enter. Then I'm going to go to the right. Press enter. And then a guess, and it kind of got cut off, but if I go anywhere in the middle there, it should be okay. -3 and 302,500. So using TI-83 max feature, maximum feature, the max is 302,500. But that's not answering the question. Find the maximum revenue. Well, that's the maximum revenue. So the maximum revenue is $302,500 per week, when the average price, when we have, I was a -3, wasn't it? Have 3 price cuts, right? So if I substitute that in my price function, my sales price function, it's 7,000 plus 500 times -3, which is actually lowering the price. Having cheaper cars gives the maximum revenue in this case. Dandy. That was a bit of fun. Now for homework. Homework, this is kind of a weird thing, because there's bits and pieces of these modeling questions all over the place. And it says do a variety. Do some composition, some products, some sums, and a couple where you're given the equation, a couple where you write the equation yourself. from all of these, a whole list, and just pick a variety. The first thing is sums and differences, products and quotients, and then, or products there, quotients there, and this will be the composition stuff. And just pick a bunch of different ones. Not all ones where you have to write the function yourself, not all ones where you're given them, not all easy ones, not all hard ones. Do a variety, please. And thank you. And then there's FAQ, and we're nearly done.